Hello, YouTube. Today we are going to tear down and try to repair this nutrition scale. It is called so because you can weigh an ingredient, then type the code of that ingredient that is provided by the manual and then get its nutrition facts like the number of calories, fat, cholesterol, carbohydrates, bread equivalent, protein content, all that stuff in their corresponding units for the weight you are measuring. And you can store that information in the memory. Unfortunately, this scale is defective and we are going to show it in a minute. I have already removed the screws that maintain the scale in one piece and we are going to remove this plate so that we can power the scale with 6 volts. And now I will turn it on and it has already started to show the problem. You see, the reading keeps changing upwards even without any weight applied to the load cell, and it does not seem to stop, or want to. So that is a fail that we are going to try to correct. Now we remove the top to have full access to the base of the housing. This is the battery compartment. We can see that the wires are tidily organized with hot glue, not hanging out in the breeze. I have already removed the screws that fasten the load cell firmly to the base. Here is a detailed view of the board. In this area here we have the power supply. Then we have a crystal, an EEPROM, a processor and an op-amp. Tucked below this crooked capacitor we have another op-amp IC. And here we have some logic gates and digitally controlled switches. The LCD and the flex cable to the keyboard. Here is a detailed view of the op-amps. This here happens to be an OP07. It is an ultra-low offset voltage op-amp, used with sensors like strain gauge Wheatstone bridges. Down there lies an LM358, which houses 2 single supply independent op-amps. And here we have a Winbond W78LE52, compatible with the classic 8051 processor, cited by this 24C01A, a 1 kilobit I2C serial EEPROM. One thing to note is the application of conformal coating on the terminals of chips and resistors. Another view of the processor with dabs of conformal coating surrounding the package. Here is a detail of the flex cable, soldered onto the board, and here we have a CD4011, a quad 2-input NAND gate, and an HCF4066, an electronically controlled CMOS bilateral switch. We can also see that there is some corrosion in parts of this PCB, which raises some suspicion on what might be there on the underside of this board. I hope the camera can capture this, but I have been tapping with this spudger on the board and noticed that if I press it at this point the reading changes a lot. So I suspect that the problem must be in that region. Let's go investigate. Well, here we have it. Corrosion over this area of the board here, directly below the NAND gates and the CMOS switches. Look at this screw here and compare it to what it should look like. This trace here is completely gone. It would end at this via, which is completely covered by debris from the corrosion. Luckily it was intended to connect an uninstalled second buzzer here. Its absence is not going to be missed. I am seriously worried about these traces over here, and after I clean up all this mess with isopropyl alcohol, I will have to check all the traces and vias for continuity. Some more detail of what seems to be sediments from battery electrolyte. One thing I do not feel comfortable with about this scale is the presence of this buzzer near the load cell, with its connecting wires crossing the wires that come from the load cell sensors. Buzzers vibrate and take relatively high voltages when compared to the very small signals that the sensors can deliver. Well, after cleaning up the board I checked every connection for continuity and all the traces tested out miraculously okay. I have not found any obvious fault that could lead to the problem we saw at the beginning of this video. I also resoldered suspicious connections and apparently the problem dwindled but did not disappear. So I decided to reverse engineer the area around the corrosion so that I could have an idea of what to look for. And that revealed the schematic, which seems to be of a DC differential amplifier and an integrating analog to digital converter. What this does is to amplify the tiny differential voltage from the load cell and then integrate the resulting signal for a fixed time. Next, it integrates a reference voltage of opposite polarity for the time necessary for the integrator to return to its initial value. This time is measured by a counter in the microprocessor and it is mathematically proportional to the mean of the input value. This technique is used in countless instruments and in almost every digital multimeter. Normally you find all of this included in a single IC, but in the case of this scale the designers decided to go discrete. By the behavior of the problem, I suspect that this must have something to do with a capacitor slowly charging up, or with a component slowly warming up like a voltage regulator, for instance. Maybe C11 is not being properly discharged and is accumulating charge from each previous integrating cycle, or there is an offset voltage produced by a mismatch of these resistors. Who knows? Well, after much poking around with multimeter and oscilloscope probes, I found this signal between pins 6 and 2 of the OP07. It comes up after the scale is kept turned off for a relative long time and then is suddenly turned on. You can clearly see a voltage drift, even more visible when we change the time base. It runs for various seconds and even minutes. I checked the power supply, straight as a precision ruler. Then I disconnected E+ and E- from the load cell bridge. With this I was sure that the bridge could not be drifting from a possible strain gauge mismatch, or some warming up due to the supply current, or a drifting from the supply voltage. The problem persisted. Then I changed C10. Could be dielectric absorption, a phenomenon by which a capacitor accumulates a residual charge over time. But nope. Then I checked the virtual ground in the reference with the oscilloscope. Nada. Then I decided to go for broke and breadboarded this DC amplifier with a new OP07. And this is what I got. Sure enough. No drifting. Consulting the datasheet, we see that this op-amp is expected to raise its offset voltage at warm-up and does so for various minutes until it stabilizes. It is also known that these parameters tend to degrade with the age of the IC. Could it be that with age this offset voltage drift would go to a point of disrupting the performance of the op-amp? Well, there is only one way to find out. As a curiosity, let me show you the waveforms we find at the output of the integrator, the integrate command from the microprocessor, and the deintegrate complete signal. The yellow trace is the integrator output. The flat top portion corresponds to the integrator being zeroed. That is, the capacitor is shorted by the parallel switch. The descending slope is the integral of the signal from the DC differential amp, which is now constant, hence the constant slope against time. The ascending slope is the reference being integrated until it reaches the initial value, when the capacitor is short-circuited again. The integration of the reference is also called deintegration. If I depress the load cell, you can notice that the descending slope gets steeper, but maintains its interval, whereas the ascending slope maintains its rate of change but takes more time to achieve the initial value. This gets a little clearer when I also show the integrate signal that comes from the microprocessor represented by the blue trace. It commands the start of the integration process by going low, and stops it by going high. And now the blue trace is the signal that goes to the microprocessor, and when it goes low it informs that the deintegration is finished. These two signals, more specifically the interval between the end of integration and the end of the deintegration, is what controls the counter in the microprocessor, and that is exactly what you see on the LCD, the result of a count, which is performed several times per second. So there you have it, the scale is not drifting anymore. We are going to weigh this aluminum slug to see if everything is hunky-dory. The scale is returning to zero. Okay. All it took was the replacement of the original DC amplifier op-amp OP07 by a new one. And here is our retired soldier, proud of its long years of good service. Thanks for watching. Have a good night and stay beautiful.